Okay, so welcome to an introduction to programming with Python, and this is our fourth lesson. In this lesson, we're going to summarize and bring together all of the key ideas that we've developed to this point, and we're going to solve the problem that we looked at last time in a different way, using a different algorithm. Last time, we found where these two graphs crossed each other by finding the x-intercepts, or the zeros of this equation. And we did that using a bisection method. And that basically involved taking an interval that we knew contained the root, cutting it in half, and then discarding the half that didn't contain the root each time. And we knew it didn't contain the root if the sign of the y value didn't change. And so you can see just by cutting these in half and then throwing away the side where the y value doesn't change, you quite quickly get quite close to the root. That was the bisection method that we introduced last time. We're going to solve this problem with this same function, finding out where it's zero, using a different technique this time. And this is an opportunity to review while loops and calculations and comments and print statements and all of the like. If we have a function here represented by a blue line and we want to know where it's zero, one way to do that is going to be to start with the value x1. That could be a guess at the root. And then to consider a tangent line drawn at x1. And notice that the tangent line, where it crosses the x-axis, has gotten us closer to that root. And if we were to repeat that process to go up here, draw another tangent line, and then we would be getting very close to that root. And then again, you would repeat it again and get another x value. And soon enough, your y value is going to get less than your error tolerance, i.e. your x value is going to be extremely close to the root that you're looking for. This is known as Newton's method. And it requires that we find the x-intercept of a tangent. Now that turns out to be pretty easy just using grade 9 math, because we know that slope is rise over run, and that's the change in y over the change in x, but from differential calculus we know that's y prime. But if we look at our slope triangle here, we see that the second y value, y2, is 0. So this calculation then, or this ratio rather, reduces to this. We also notice that we're evaluating the derivative at x1. So our tangent line is drawn as x1, so this slope is y1 prime. Now if I rearrange that and solve for x2, we'll cross multiply this up, cross multiply this down, and we'll get x2 minus x1 is minus y1 over y1 prime, which, if we solve that then, just give myself a bit more room, for x2, which is the second x value, we see that x2, the new x value, is the old x value, bring this over to the other side, minus the old y value over the old slope. So I make that a little more tidy. That's y1. And this is y1 prime. Now, we can extend that, and not just for x2, we could say the new x value, like x3, will be x2 plus minus y2 over y2 prime. And then the fourth point will be x3 plus minus y3 over y3 prime, where this is the y value corresponding to x3 and y3 prime is the tangent slope. So we just repeat this process over and over and over again, where the run is y over y prime. So this lends itself fairly easily then to a computer program. And here's the code, and this is set up for you to read, have a look at it, try and understand what it does, and then try and write this code yourself starting from scratch. So good structured programming, first of all we import our libraries. we'll need the numerical library. I don't think we end up needing the graphic library here. We'll set the precision of the tolerance. We're going to want the y value to be this close to a root, to 0. Here for Newton's method, we need both the function and its derivative, and we have to input these manually. So here's the sine x minus x over 2, and then here is y prime. I just did the derivative. The derivative of sine is cos, the derivative of x over 2 is a half. Now, why do we define functions like this? Well, it just saves us from having to write this expression over and over and over again, because it's easier to write y than it is to write np.sin x minus x over 2. So you'll see down here in the actual program, I can just write y of x and I can write y over y prime instead of having to put that whole expression in there. And it just makes it more readable, and it also kind of makes it easier to understand what I've done here. So we define these functions, and this is the syntax for defining a function. Anytime you're going to calculate some sort of mathematical expression more than once, it makes sense to define it as a function in this way. Notice there's an indent here, just as for loops. Notice that the final statement in a function has to be return, and that's the value that gets sent back from the calculator. These little functions are just like calculators. All right, here's the main body of the code. Newton's method needs an input, so we always start with an input statement. And then here we have a while loop. Similar to last time, we're going to loop as long as the y value is greater than precision, because that means that if the y value is greater than that, then we're not as close to the root, we're not as close to the 0 as we want to be. Here is our statement. Now this looks a bit weird in computer programming, but it says the new x is the old x minus the old y over the old y prime. That's exactly what we wanted. I've put in a print statement here just so you can see as it gets closer and closer and closer to the root. It's just sort of nice when you're doing the programming to put the print statement in there and make sure everything's working properly. This is really not necessary. We see that the loop ends because the indent has ended, and at that point the while loop is finished. That means that the y must be within 0 of our must be within precision of 0, and our precision here, I set it up here to be 10 to the minus 4. So then we're ready to output results. So there's a print statement, and then notice that there's lots of nice comments here, good structured programming. There's several things that we can see. The use of comments, making good variable names like y and y prime. Anyone looking at this knows right away what it is. Precision, again, another good descriptive variable name. And then the breaking the code into chunks and sort of a standard order. You know, you import your libraries, you set your constants, define your functions, then you've got a main body of code, and then you've got output at the end. So that's good programming practice. So for our lesson today, we're introducing another way of finding a root of a function using Newton's method. We're using a while loop then to iterate that process, and we're defining some functions and making lots of comments and doing all the things that we should do to have a good structured program that somebody can read. So have a look at this code, understand it, and then try and duplicate it yourselves. That's the task at this stage, to bring together everything that we've covered so far.